Watch this steel ball roll down this curved ramp. Gravity pulls it, and its speed increases as the slope drops. This diagram shows a standard Cartesian coordinate plane, with a straight diagonal line representing the linear function y equals mx plus b. The defining feature of this straight line is its constant slope, represented by the variable m. If you calculate the rise over run at the bottom, the middle, or the top of this line, the result is identical. The rate of change remains the same. But when we update the formula to a quadratic function, ax squared plus bx plus c, the straight line bends into a smooth U-shaped parabola. As long as the leading parameter a does not equal 0, the squared term guarantees the resulting geometry will curve. Because the geometry curves, its rate of change becomes a moving target. A tangent line sliding along this parabola tilts steeply upward on the right, lies flat at the bottom, and points downward on the left. How do we calculate a precise algebraic rate of change when the rate never stops changing? By deriving the formula for this shifting slope, we can pinpoint exactly where the curve reaches its lowest point or crosses the horizontal axes. This diagram shows a target coordinate, x sub 0, on our parabola. We must calculate the specific slope at this exact location. Instead of relying on a traditional calculus limit, we can bracket this specific point using a symmetric interval. We move horizontally forward along the axes by a small fixed distance, h, marking a new point on the curve at x sub 0 plus h. Then we move horizontally backward from our original coordinate by that exact same distance h, placing a third point at x sub 0 minus h. Connecting these two outer boundary points creates a straight secant line passing through the curve. The slope of this secant line provides an approximation of the exact slope at our original target point. To find that slope, we set up a rise over run calculation. The vertical change, the rise, is the difference between the two boundary function values. For the horizontal run, since we moved forward by h and backward by h, the total distance is 2h. This symmetric difference quotient allows us to compute the slope for any curved function using only the original coordinates. This split screen diagram displays our parabola on the left and the symmetric difference quotient on the right. We merge the general quadratic equation into this formula, expanding the numerator by substituting our boundary coordinates into the standard form ax squared plus bx plus c. Because the interval is symmetric, several variables will naturally mirror each other across the minus sign. The squared x terms, the squared h terms, and the c constants subtract to 0. The algebraic expression collapses to a simple remaining numerator, 4ah x naught plus 2bh. Finally, we divide out the common denominator of 2h, which removes the variable h from the expression entirely. The resulting expression, 2ax plus b, is the generalized rate of change for any quadratic function at any point. What happens to the curve when this shifting rate of change hits 0? A slope of 0 indicates a flat horizontal line. It happens at the moment the parabola stops going down and starts going up. Setting 2ax plus b equal to 0 and solving for x isolates the coordinate x equals negative b over 2a. Dropping a vertical line at this coordinate defines the axis of symmetry, identifying the lowest point of the parabola. Since 2ax plus b equals 0 identifies where the slope is flat, negative b over 2a defines the extreme peak or valley of the curve. We can now apply this vertex formula to predict where a function intersects the x-axis. This three-panel diagram displays three distinct quadratic equations to test the model. In all three equations, the leading coefficient a is a positive 1, meaning all three parabolas will open upward. For the first equation, we plug its coefficients into negative b over 2a. This locates the vertex at x equals negative 3, with the lowest point sitting below the 0 line. Because this vertex sits below the x-axis and the curve opens upward, it must cross the axis twice, yielding 2 real roots. In the second equation, calculating negative b over 2a places the vertex exactly at negative 1 on the horizontal axis. When the lowest point of the curve rests on the 0 line, the vertex itself acts as the single solution. In the final equation, our calculation locates the central axis at x equals 0. This places the lowest point of the function strictly above the x-axis at positive 1. Since it opens upward from this elevated baseline, it will never intersect the x-axis, yielding 0 real roots.
The formula for variable slope translates raw numerical coefficients into a predictable geometric reality, revealing the behavior of the curve through algebra.